Hello everyone, today starts our first day in our new section, which is going to be 5.4. We'll call this our day 1 notes. Solving exponential equations. Using logarithms. To do this, we'll be using a similar idea to how we wrote inverse functions. We will either raise both sides or log both sides. And that's a key idea, so if you have your highlighter, I would highlight this piece right here. It's going to be the key tool in our toolbox for solving these equations. And then one note on solving an exponential equation. So when solving an exponential equation, we will either log both sides or make the bases equivalent. So with these two notes in mind, let's actually get right into our examples. The directions are very simple. Solve. Number 1 says 1/2 10 to the 2x minus 3 plus 4 equals 21. And I'm hoping that as you're writing, we're paying very careful attention to what levels we are writing our terms. So if you look here, I clearly did my absolute best to keep 1/2, this base 10, the plus 4 and the equals 21 larger and on the same level. 2x minus 3 is clearly raised and written a little smaller. That really is important because otherwise we might mix up what's a base, what's a power, what's a term. Like here, this plus 4 is something we're about to do something with, but if by accident I wrote it small and up here, I wouldn't realize that that's what I need to do first. So be conscious as you're writing these notes and these solving steps. Now our first step has not changed. Just like when we were working with inverses, we worked to, after we switched x and y, we worked to isolate the log term or isolate the power term. We're going to do the same here. So before we get into the actual log part of the solving, we have some algebra we can do. First, always ask yourself, is there something that you could add or subtract? Well, I see this plus 4 here, so I can subtract 4 from both sides. That leaves 1/2 10 to the 2x minus 3 equals 21 minus 4. If, by the way, you don't have your calculator out yet, please get it out because I want you do the math first before I do it. So mental math though, 21 minus 4 is 17. Our power term is not completely by itself yet because we have this 1/2 out front. So I can address that by doing what? What will I do to both sides to get rid of that 1/2 using my algebra skills? Well, I know the reciprocal of 1/2 is 2, so I can multiply both sides by 2, and that's super helpful because 2 times 1/2, any number times its reciprocal is 1, so that cancels. That leaves behind 10 to the 2x minus 3 equals 17 times 2, 34. Now, at this step, I have to ask myself, is there anything else I can do with addition, subtraction, multiplication, or division to go any farther to get to x? And the answer is no. So we need to have a new tool in the toolbox. And that's where when we go up to what we wrote here, we will either raise both sides or log both sides. So here I already have 10 to a power. So to undo an exponent, using the inverse operation, I will log both sides. Now we get to choose the base because we're doing it to both sides, we get to pick. To be strategic, if I see 10 is the base here, I am going to choose to do log, oops, I don't mean to write that there, log base 10. So I'm not going to write the base 10 because we know that with our common logarithm, it's there. I am taking the log, that's messy, of both sides. And for me, in my notes, to help this stand out, I actually highlight, oops, that's not what I wanted. I actually highlighted this. Once I wrote it, I highlighted it so it stood out. So I realized that that's something that I chose to do to both sides. What's the advantage of doing this? Well, log base 10 of 10, from our properties we know that that cancels. Or you could also mentally think of it as the power property at work, where 2x minus 3 would come out front, and that would be 2x minus 3 times log base 10 of 10, which again, log base 10 of 10 is 1. So no matter how we look at it, we're left with 2x minus 3 equals log of 34. In this step right here, we have successfully unlocked that power, that x, that was in the exponent spot. And now we can just finish solving for x. So to solve for x, we will add 3 to both sides. Remember that we cannot touch the argument. So that's going to be 2x equals log of 34 plus 3. And then to wrap this up, we will divide both sides by 2. That's my exact answer. Go ahead and type that into your calculator and let's see what we get as a decimal approximation. Remember that the numerator, we will need to use parentheses before we divide by 2. Press pause until you have it, and then check with me. That is approximately, so I changed my equal sign to a squiggle equal sign, 2.266. So I have an exact answer and a decimal approximation. Let's work on number 2. Number 2 says 5 to the x plus 2 plus 3 equals 25. Our first priority is to isolate the power or log term. So in this case, my power term is 5 to the x plus 2. So the very first thing I will do is what? What do you think we're going to do first? we are going to subtract that 3 over. So I have 5 to the x plus 2 equals 22. Once again, at this point, I'm trying to get that x by itself. Adding, subtracting, multiplying, and dividing fails us. So we can either raise both sides or choose to take the log of both sides. This is already raised, so to undo an exponent, I will use logarithms. Once again, I want to be strategic. So if I see that this is 5 to a power, I'm going to choose to do log base 5 of both sides. I'm going to be changing the pen color because overwriting it in yellow every time is going to be a little arduous for me. What I put in blue is what, if I was writing in pencil, what's in blue I would highlight to make it look like that in my notes. So we will take log base 5 of both sides. Using our inverse properties, log base 5 of 5, that cancels out, leaving behind x plus 2 equals whatever log base 5 of 22 is. Now remember, this is a decimal. I could use change of base and figure out what log base 5 of 22 is. But for neatness and accuracy, we will let it just stay log base 5 of 22 for right now. To finish solving for x, we will simply subtract 2 from both sides. We get x equals log base 5 of 22 minus 2. So that's my exact answer. Please go ahead and find your decimal approximation. Press pause until you've got it and then check with me. Remember, because this is not base 10, we will need to use change of base. In case you needed help with that, in my calculator, it's going to be log of 22 divided by log of 5 minus 2. We should be getting negative 0.079. Moving on to number 3. Four plus e to the negative x equals 6. Once again, our first step is to always isolate the power term. So we will subtract 4 from both sides. As soon as I see e, I always want to think of its inverse, which is natural log. So this is as isolated as I can get this power term. We are now ready to take the natural log of both sides. Natural log of e, those are inverse operations. Also, you can remember, you could apply the power property here. That becomes negative x times natural log of e. Natural log of e is 1. We are left with negative x equals natural log of 2. So just a side note, you can either do L, like a non-cursive L, or cursive L. Totally up to you, what you like. To finish solving for x, we're so incredibly close. We will divide both sides by negative 1. Remember that any algebraic operation that we do, it never touches the argument. So this does not become the natural log of negative 2. That negative comes out front. We have negative natural log of 2. Go ahead and get your decimal approximation. using your calculator. We should be getting negative 0.693. Number 4. 4 to the 3x equals 8 to the x plus 1. Isn't this one interesting? Oops. So interesting, I moved past it by accident. Alright. As soon as I see a situation where I have powers on both sides, my first thought will always be, can I rewrite this with a smaller base? Preferably the same base. So I know that 4 and 8 are connected to base 2. So let's see how this is going to work out. I can rewrite 4 as 2 squared. That 3x is still there as a power. And I can rewrite 8. How can I rewrite 8 as 2 to a power? I'm hoping we're saying 2 to the third. And then this x plus 1 is still a power on the outside. Remembering our exponent properties from way back, power of a power we multiply. So this becomes 2 to the 6x. And on the right side we have 2 sending in or distributing 3. This becomes 2 to the 3x plus 3. If these bases are equal, that means that their exponents also have to be equal. So we get to say, well, the bases are equal, so I'm going to set the exponents equal. 6x equals 3x plus 3. And now we can solve for x. We will subtract 3x from both sides. Oops, that's funny. 3x equals 3. And then to finish, we will divide both sides by 3. And we're done. Number 5. (27 to the 1 minus x equals 1/9 to the 2 minus x. Again, strategy, and this is not always going to be possible, by the way, but the go-to strategy is if it is possible, rewrite the bases to be the same, because once I have the same bases on either side, I can set the exponents equal. When I see 27 and 1/9, I'm hoping that we're thinking of base 3. So how can I rewrite 27 as 3 to a power? 3 to the third is 27. 1 minus x is still an exponent up high. Equals, how about that 1/9? How do I write 1/9 as 3 to a power? Well, I know that 9 is 3 squared, so that means 1/9 would be 3 to the negative 2. Remember, negative exponents get us fractions. So I can rewrite this as 3 to the negative 2, and again, 2 minus x is still on the outside. Power of a power we multiply, so 3 times 1 is 3, 3 times negative x is minus 3x. So I have 3 to the 3 minus 3x equals, what am I going to get on this right side? You decide. What do we get on the right? Distributing negative 2 to both of those terms, this becomes 3 to the negative 4 plus 2x. Again, once I have same base, that means that their exponents have to be equal. So 3 minus 3x equals negative 4 plus 2x. go ahead and finish solving for x, and then when you're ready, compare answers with me. So press pause until you're done. Again, when you press play, I will continue through to the solution. So first, I'm going to subtract 3 from both sides. We get x equals 7/5. I'm going to erase this little note so it doesn't take up too much space. Number 6. Number 6 is going to be the third root of 8 to the x plus 1, all divided by 16 to the x, equals 32. How awesome is this question? So let's get started on it. What are we going to do first? Well, as soon as I see third root, my first thought is maybe write it to the 1/3. What I mean by that is remember that third root equals whatever's there to the 1/3. At the same time, I also see 8 to a power and 16 to a power. Our strategy, our go-to strategy if possible, is still the same. Can we write 8 and 16 with a smaller base? 8 and 16, from our prior knowledge, are both connected to 2 to a power. So 8 we can rewrite as 2 to the 3rd raised to the x plus 1 divided by, how about 16? 16 I can write as 2 to what power? 2 to the 4th. So all I did from here to here was rewrite 8 with a smaller base and 16 with a smaller base. Haven't actually done any other algebra than that. But I have to remember that all of this is raised to the 1/3. 2 is our go-to base at this point. Can I write 32 as 2 to a power? Yes, I can. Think about it. Think. 2 to what power is 32? Pause and figure it out if you're not sure. Two to the 5th is the answer. 2 to the 5th is 32. Now, again, from here to here, I have done no other math other than rewrite 8, 16, and 32 with a smaller base, all base 2, and then instead of dealing with the radical notation, I chose an exponent notation. Now let's get to work. I hate this 1/3 out here. That's ugly. No thanks. So what can I do to both sides to cancel that 1/3? I can raise both sides to the 3rd power. Notice how space is my friend. Look how much space I used to show my brain this step. Space is good. So 3 and 1/3 cancel because that equals 1. And let's see what's left. Power to a power, I know I can multiply, so that becomes 2 to the 3x plus 3 divided by 2 to the 4x equals 2. 5 times 3 is 15. I have the same bases everywhere. So once again, their exponents have to be equal. When we're dividing, we're using our quotient property, which means we do what with the exponents? Quotient property says when bases are the same, we subtract the exponents. So 3x plus 3 minus 4x. If this had had anything else, by the way, I would have made sure I used parentheses. So just for good habit, I'm going to throw them in there. That has to equal 15. And from here, I can just use my algebra skills. Combining like terms, 3x minus 4x is a negative x plus 3 equals 15. We'll subtract 3 from both sides. And then last but not least, divide by negative 1. And we get x equals negative 12. So there really weren't many steps, but the key was allowing my brain to use space as my friend, don't crunch everything, and the key was to write with a smaller base. And then remember the other exponent skills we have in our toolbox. Number 7. Says 6 to the 2p minus 3 times 4 to the negative 2p minus 2 to the 4th equals 0. So again, 6 to the 2p minus 3 times 4 to the negative 2p minus 2 to the 4th equals 0. As always, our goal is to isolate the exponent term, or the base, the exponent, however you want to say it, the power term. So here we've got 2. These guys right here. They do not have the same base, so we cannot touch their exponents. But this negative 2 to the 4th, I can move over. So this will become 6 to the 2p minus 3 times 4 to the negative 2p equals, adding 2 to the 4th over to the other side makes this equal to 16. Now I have some decision making to make because, what do I do? I've got 2 different bases. I've got 6 and I've got 4. Well, we're going to have to make a decision. Either log base 6 or log base 4. I choose log base 6, and there's no specific reason to that. You could do log base 4 and work it out the way we're about to do it, and you will get the same answer. But you have to commit to one of them. You can't do both. So we'll take log base 6 of both sides. This line going. Using our expanding properties, multiplication becomes what operation? Hoping we're all saying addition. So when I break this up, it's going to be log base 6 of 6 to the 2p minus 3 plus log base 6 of 4 to the negative 2p. This is where it's really important that the exponents really look like exponents. So for example, right here, I kind of made that a little bigger than I wanted, so I'm going to back it up and make sure it stays super small. And then log base 6 of 16 will stay. From here, let's see what happens. Log base 6 of 6, those are inverse operations, those cancel. We're left with 2p minus 3 right there. Log base 6 of 4 does not cancel because those are not inverses of each other, but we can apply what property? We can apply the power property. So bringing that negative 2p out front, that'll become negative 2p log base 6 of 4 still equals log base 6 of 16. Space is our friend as we go from step to step. just as if, think back, as crazy as this looks, this is no different than if I had 2x minus 3 minus 2x. Sorry guys, I'm just checking out something real quick. Yeah, I'm in good shape. Equals, I don't know, 10. We want to get all of our variables on one side and numbers on the other. So remember, this is a decimal we just don't feel like writing out. This is a decimal we just don't feel like writing out. Don't let the logs intimidate you. So anything that doesn't have a p with it, like this whole term has to stay because p is here. 2 times p times log base 6 of 4. That's all together. But see this, oh, that's not our bell. Sorry, it's in the video. This 3 at the end, I can move that. That 3 I can do something about. I can add that to the other side. So now I have 2p minus 2p log base 6 of 4 equals log base 6 of 16 plus 3. I have two terms that have a variable in it. So I can factor out p. When I factor out p, what's left? Well, I've got 2 minus 2 log base 6 of 4 equals, this is still here, stays along for the ride. And now how can I finish solving for p? Well, to finish solving for p, we can divide this over. So I'm going to divide both sides by 2 minus 2 log base 6 of 4. So this all cancels, leaving behind p equals log base 6 of 16 plus 3 divided by 2 minus 2 log base 6 of 4. Now that's my exact answer. To actually get this decimal approximation, I recommend we use the store feature to help ourselves out. So I would store this as x, and I would store this as some other letter, whatever you want. So what I mean by that is change of base. We're going to do log of 16 divided by log of 6. In your calculator, store that for x. Then over here, do log of 4 divided by log of 6 and store that for whatever you want. Like let's say you make it r, whatever you want. Because once you have that stored in your calculator, you're able to type in, this is now represented by x, this, if you do choose to use r, is r. You get to type that in instead of trying to tackle this big guy all at once. I'd like you to press pause and give that a shot. When you press play, I will let you know what the decimal approximation is and we'll see if we match. The decimal approximation is 10.048. So if we didn't get that, no worries. Please show me what you've got in class tomorrow and we will take a look and see what's up. Number 8. Says 2 to the x plus 3 equals 3 to the 2x. So once again, I have the situation where I have a power a base to a power on both sides, but notice, are the bases the same? Nope. So we're going to have to commit either log base 2 or log base 3. For these notes, I choose to go log base 2, but you could totally go log base 3 and you should get the same answer. Just the work to get there will be different. So I'm going to do log base 2 of both sides. I'm just going to set this up for myself with the blue so it stands out. Oops. So notice, you cannot do log base 2 here and then, oh, I want to do log base 3 on the right. Nope, can't do it. Has to be the same log base number. Log base 2, both sides, or it's a very long bell. Log base 2 both sides, or log base 3 both sides. Now from here, let's see what happens. If you're good, by the way, to press pause and give it a shot, taking this from here to the end, please do that. Press pause right now and give it a try. Those of you who are staying with me, at any point that you're comfortable to finish the rest, again, press pause and go for it. So I see log base 2 of 2. Log base 2 of 2 to anything, well, that's an inverse operation happening right there. That will cancel, leaving behind, cancel it the other way, so not cross out the 2. Leaving behind x plus 3 on the left side. On the right side, it's not going to be so pretty because log base 2 of 3, those are not inverses, they will not cancel. But we do have the power property that we can use. And this will become 2x log base 2 of 3. Remember, don't let logs scare you. They are just ugly, ugly decimals we don't feel like writing out. So when you see log base 2 of 3, I want you to think of it just like if that was an 8 or a 6, like any other number that in this case just happens to be a decimal. We have x present on both sides. We want x to be on only one side. So this guy's already over here. This counts, guys, as one term. 2x log base 2 of 3. That is one term. I will subtract this x over. So this becomes 2x log base 2 of 3 minus x. Recall that terms are separated by addition or subtraction. So like now over here I have two terms. I see x present in both of these terms. So thinking back to number 7, what strategy are we going to use now? What did we do right there? How did we get from here to here? Horrible use of arrows. How did we get from here to right there? Well, up here when we saw p present in both terms, we factored it out. So same thing's going to happen here. Let's factor out x. That will leave behind 2 log base 2 of 3 minus 1. These are now factors. X times this. So these are now factors, which means I can now divide by that factor. And we get x equals 3 divided by 2 log base 2 of 3 minus 1. Once again, I recommend that you use your store feature to help yourself out to get your decimal approximation. So to help myself out with that, I would say, well, I'm going to let my calculator say, do my change of base and store log 3 over log 2. Let that be x. Then in my calculator, I would just need to do 3 divided by 2x minus 1. So give that a try. Once again, press pause, and then we will check our decimal answers together. When you press play again, you will see my decimal answer. The decimal approximation here is 1.383. If we're having any struggles with the calculator, don't sweat it. We'll talk about it tomorrow in class. Last example for today is number 9. Number 9 says 2e to the 2x minus 5e to the x minus 3 equals 0. This is quadratic-like, in the sense that I have 3 terms. I have a squared term, single power term, and a constant. So we will be bringing back U substitution. U substitution is a tool in our toolbox that helps us let U equal a value, work on the solving, and then plug U back in. So for this example, let's see. Well, the term that's present in both is e to the x. I have e to the x right here and e to the x right here. So we're going to let U equal e to the x. Let's see how nice this becomes when we do that. So 2e to the 2x, that will become 2u squared. Minus 5e to the x becomes minus 5u, and that minus 3 is still along for the ride. Now I clearly see that this is a quadratic I can factor, hopefully. A is not 1, so recall guess and check inner, outer equals middle. I'm going to, by the way, highlight this. I would highlight U substitution so it stands out in your notes. Remember, A not 1. So it's going to be 2u and u. So go ahead and figure out that factor combo that will work. We get 2u plus 1 and u minus 3. If we didn't get that, by the way, let me know if you need some extra factoring practice and I can print that out for you. From here, we will split this up to be 2u plus 1 equals 0, u minus 3 equals 0. Solving for u, this will be u equals, what do we get? Let's see, we get negative 1/2 over here. And here we get u equals 3. We are now ready to plug u, this is a u, plug u back in. So this becomes e to the x equals negative 1/2, and this becomes e to the x equals 3. And these are like little baby equations I can solve pretty quickly. We will take the natural log of both sides. I'm trying to stick to my colors here. Natural log of e cancels, leaving behind x equals natural log of negative 1/2. We can never take the log of a negative. So when you type this into your calculator, you should get this error message back that says no solution or error. So we cross, even though this is technically an algebraic answer we get, that does not exist. Let's see what happens when we do this side. Natural log of e to the x equals natural log of 3. Natural log of e cancels, leaving x behind. Natural log of 3 is a value that does exist, and you can either say x equals natural log of 3 or give me the decimal. I'd be fine with either. So we do have a solution. This is the real solution that does exist. And that completes our first day of solving notes. Great job. Any questions, please pause the video at any time. Go back, take a picture, shoot it to me on Remind, and I will help you out. Have a great night, guys.